Hey everyone. From the last video, we showed how we could use a neural network to approximate the exclusive OR function, or in this case we actually got it exactly, but we can use neural networks to approximate just about any function, and we want to be able to do that in code, because drawing this out by hand and doing the math by hand sucks, it's inefficient, we're going to get things wrong. Alright, so how do we do this in code? We have to start with nodes and connections, so let's just get writing. We're going to start with the node class. And the node class has a few things we need. We need a value to store the current value of the node. We need a bias value to add to all the incoming values coming in. And we also need an X position. The X position is a little bit funky. If we go back to our image, these input nodes are going to have an X value of 0. As we get further to the right, we're going to get to, say, 0.5, and then 1.0 here. This is just something really important for sorting, because as we flow from left to right, that's the order that we do our calculations in. Alright, so let's write our constructor. So our node really just needs to take the X value, because the value and the bias will be set later. Alright, but let's write getters and setters real quick. If you're new to IntelliJ, you can use Alt Insert or right click anywhere and call generate. And this is good enough for now. So now we have nodes that are floating out somewhere. Or we don't even have nodes floating anywhere yet, but we have the concept of a node. How do we connect nodes to other nodes? A very, say, naive approach would be to think back to a linked list and say private list of node, and then say incoming nodes. And this way we would have our node class that would store a reference to all of the previous nodes. So if this is our node class, we could store a list of the input nodes here, and this could work, but how do we want to store connection weights? I suppose we could store a second list, but then we get into some other annoying issues, and it's better to just create a wrapper class. So instead of having a list to our references, and creating a really linked list style structure, let's create a separate connection class. Alright, so our connection is going to have a weight, but more importantly than that, how do we connect our nodes together? Well, we have to flow from a node, and we have to connect to a node. Alright, that's it really. From there we can just create our constructor, which I will generate because I am lazy. And we can have getters and setters for everything. The connection is really just to store some data, so we will never come back to this class. All of this data is good. We're never going to add new methods. Alright, so we have now a way to create nodes and connections, but how do we actually connect one node to the other? So let's create a method for this. I'm going to zoom in so we can see it better. Over here, we're going to have a method that returns our newly created connection, and we're going to call it connect. And we need to have some target node to connect to. All we're going to do in this method is first instantiate our connection, and we're going from this node to the target node. And we don't really need to set anything. You could explicitly set the weight to 0, but that's already there by default. All we really need to worry about is actually storing the connections in the node. So right now, we don't have any way to do this. Just like how we thought about before with the list, we can have a list of incoming connections. So let's have a list, of course import that, and we'll have incoming connections. Make sure that we instantiate this array so we don't get any null pointer. And here, this represents all the connections that are flowing into this node. So we want to take our target node and then add it to add our newly created connection to the incoming connections to the target node. It's a very easy mistake to make here to say this.incomingConnections.add, but that would imply a right to left direction instead of a left to right, which of course would be pretty wrong. And we can just return our connection, and we're all good. From here, we can create a method to actually predict values, right? Because we can connect our nodes now, but we don't have any functional value to our neural network yet. So let's add some functional value. We're going to create a new method to predict what the current value of this node should be. And what we're going to do is sum up all the values, right? Because there's 2 steps. So step 1 is to sum up all the current values. We can't start the sum at 0 though, or we can, but it makes more sense to start the sum at the bias value of our current node. And then we need to go through every connection. We'll say connection, incoming connection, in the incoming connections. We'll say incoming value is going to be the incoming connection from node, and then the value of that node. And then we can just add that to the sum. Though importantly, we have to add in the multiplier by the connection's weight, because the connection's weight is the most important part of the neural network. That's what gets learned over time. So we should go incoming connection dot get weight. All right, so now step 2 is that we need to do the activation. So in order to activate, we have a couple of options. In our model here that we use to create our neural network for exclusive OR, we just used ReLU activation, which of course means that we have our activated value, and we have to take the biggest number between 0 and sum. This way, if our sum ever gets negative, it just bottoms out at 0. And that's the ReLU function right there. And now we can set our current node's value to our activated value. Okay, so to reiterate, this node class now has 2 custom methods. Right now it just stores some data, but if you call these newer methods, you can connect from a node to a new one, and it creates a new connection. And we can also predict the value of our current node based off of all of the incoming values. So now we have a way to be functionally useful, but how do we actually feed in values from the start and get values out at the end? Well, let's create some sort of wrapper class to handle that for us. I typically see people call it something like calculator, so we'll stick with that. But of course you could also use neural network here. All we need to store here, well, we need to store a lot of data really. We need to store the whole neural network, which means all of the nodes. So to do that, we should store 3 lists. We should store 1 list for all of the input neurons, so we'll say input nodes. We need a list for all of the hidden neurons. And we need a list for all of the output neurons. We should take all of these in the constructor. So to avoid any confusion, let's just use the generate method. And we don't need any getters and setters here. We should never really be accessing this data raw. Instead, let's create a new method to predict an array of values. So say if the output nodes is a list of 10 nodes, then we'd expect this return value to be 10 doubles. And we should be predicting based off of a bunch of input values, which will correspond, of course, with the input nodes. So let's say input values. All right, so now how should we feed these input values into our neural network? Well, each node has a setter for value. So all we need to do is iterate over our input values. And then we go into our input nodes, get the current node, and set its value. All right, so now we have a way to fill in the values for the inputs. But now we need to actually do some predictions. So if we go through every single hidden node, we can simply call the predict method that we already created. But there's an issue here, right? What if hidden nodes is not sorted left to right? We could just ask the user to always make sure it's sorted, but I don't trust them. So it's always a good idea to sort our list here. What we can do is use some Java syntactic sugar to compare off of the node's x value. And this will sort it left to right. All right. Last but not least, we need to actually return our outputs. And to do that, we should create a new output values array, which will fill up based off of our output neurons. And of course, it should be the same size of our output neurons. And now let's do the same thing we did over here with our input values. But there's a little catch here. So we need to take our output neurons and we need to predict their current value. Since the hidden nodes are different than the output nodes, we haven't actually called predict on it yet. So we should call predict first and then query their values. So let's say output values at I is equal to the current output node's value. All right, perfect. Now we can just return that. All right, so this should be a fully working system. Let's create actually let me zoom out so you can see everything in case something's not clear. All right, so now we can create one final class. We'll just call it main, and this is where we'll do all of our test work. So if we have a main method, we need to create, just like in our calculator, 3 lists. Because we need to build up our neural network. So we'll have a list of nodes for our inputs, input nodes. And we'll just use an array list for now. A list of node for our hidden nodes. And same thing for our output nodes. Though it would help if I could spell correctly. All right. Now thinking back to our exclusive OR network, we had 2 input nodes, 1 hidden node, and 1 output node. So let's do all of that. So we're going to have node input A. And remember that all input nodes should probably have an X value either really low or just 0. 0 makes it easy. Same thing with our input B. And of course the X value should be 0 because they're lined up. And now we can add this to our list. I used get for some reason. All right, now let's just worry about the same thing for hidden nodes and output nodes. So let's say hidden C is equal to new node. And we can't use 0.0 here. Typically you'll go somewhere in between. We're going to use 0.5 because that's directly in between, but as long as it's anywhere in between 0 and 1, you're good. So now we can add this to our hidden list. And last but not least, we'll do the annoying copy-paste work for output D. And again, the X value should be the big number. So in this case, 1. All right, so now we have all of our lists, and we're ready to create our calculator. So if we instantiate our calculator and make sure we fill in the correct lists, so you see here we have our inputs, hidden, and output nodes. Make sure you pass in the correct list. And we're ready to predict our methods, or we're ready to predict our outputs and see if we did everything correctly. But right now, we just have nodes floating out in space. Right, there's no concepts of connections between them because we never called connect. So let's create those connections. Input A, so first we'll look at the inputs that were connected directly to the outputs. So we're going to connect our inputs directly to the output. And we know that the weight of those should have been 1. If you're confused as to why we're choosing these values, you should definitely check out the previous video, which explains how we can solve XOR using a neural network. All right, so now we can connect our second input with the same weight. And we'll do the same thing. Well, this is all of our connections to our output nodes from our inputs. But now let's worry about the hidden node. So let's say these are our direct connections. And now we can worry about our hidden connections. Direct connections and hidden connections are not actual terminology, by the way. This is just something for clarity. So if we connect both of our inputs to now our hidden node, remember these weights were also 1. Same thing with the second input. But then we have to worry about connecting our input node, our hidden node to the output node. And this had a different weight. So if we take hidden C dot connect to output D, and this way we can set the weight to -2. And this will match up our neural network. There's one last thing here, and that's bias. We set the bias to 0 by default, and that's what we want for most of our neural network. But the hidden connection specifically needs a bias of -1. All right, so now we're ready to actually do the connections, or actually do the calculations. From here, we can set up some input array. We'll say input values. And let's try 1. No, let's start easier first. Let's go with 0, 0. So these are our two inputs. Input A will be this 0, and input B will be that 0. And now we can take our outputs, and that'll just be calling our calculator predict method and passing in our inputs. And now let's just have some way to check what the output value actually was. And we'll just use the first output value list, or the first index, the first element of our array, because we will always expect to have only one output, because we only added 1 to the list. All right, so let's run this method. If all goes according to plan, we will see 0 is equal to 0. And let's see what we get. If I scroll in, you see that we have output 0, and that's exactly what we wanted. So let's try some other ones. If we try 1, 0, then we should get 1, and we see we got 1. Awesome. Let's try 0, 1, which should be the same since we have a symmetrical neural network, but let's just be let's just check every case here. Let's be thorough. All right, so that worked. And now we can try 1, 1, and we expect to see 0, and we did actually get 0. So now we've exactly replicated our neural network from the previous video. All right, sweet. I hope this clears up any confusions, and hopefully you can now pause the code at any time and see every single class and exactly what may have gone wrong when we did it live. I'll zoom out here so you can see everything, though that's quite small. And last but not least, let's check main again. All right, sweet.